Hello everyone. Today we're looking at solving differential equations. I was originally thinking I might do this in one longer video because I really like differential equations, so therefore vicariously you like differential equations too. We're not going to do that though. A big part of the reason I like them is because Schrodinger's equation is a differential equation. So after watching this, you will hopefully be well on your way to studying quantum mechanics in a meaningful way too, rather than approaching it with pseudoscientific woo. So here's a few examples of differential equations. The first one here represents the rate of change in y with respect to x. The second one could represent the rate of change in height with respect to time. And the third one could represent the rate of change in temperature with respect to time. If the differential equation is known, then it's sometimes possible to determine the relationship between the variables themselves. So for example, if we have dy dx equals 2 over x, possible relationship between y and x would be this. So where did this derivative come from? It would have come from 2 ln x plus some constant to be determined. The other one, dh dt, is negative 10t plus 16. Possible relationship between h and t. Again, where did this derivative come from? It would have come from negative 10 over 2 t squared plus 16t plus some constant of your choosing. So we could reduce this, right? But ultimately the derivative of this would give negative 10t, so that's what we need. So for the last example, dt dt, possible relationship between capital T and lowercase t, we need to figure out where this derivative came from. It should have come from a cos, 2 pi over 365t. If we took the derivative of this, it would be negative sine this whole argument. So in order to get rid of the negative, we should probably have a negative in our original function. And if we were to do chain rule on this, it would be 2 pi over 365, but we have 24 pi over 365. So we would need to multiply it by 12 as well. And on top of that, we should have a constant. So the solution to a differential equation in two variables is an algebraic equation that relates the two variables. The equation can then be used to answer specific questions concerning the variables. As you can probably see already, the solutions will involve antiderivatives. The characteristics of the differential equation will indicate a method that can be used to find the solution. So let's move on to some examples. The differential equation dt dt, given before, represents the rate of change in daily average temperature in some Alberta town where T represents the average temperature T days after January 1st. If the average temperature on January 1st is minus 6 degrees Celsius, then determine the average temperature on June 1st. So we already know where this derivative came from. It came from this expression, negative 12 cos 2 pi over 365t plus c. And we have an extra bit of information given here. Given that lowercase t, time, is given in days after January 1st, January 1st works out to be t equals 0, and we have an initial condition on January 1st, so the temperature when t equals 0 is minus 6. So with this information, we can figure out what c should be, because if we put t equals 0 here, and put this in for capital T, then we can just solve for c. So negative 6 equals negative 12 cos of, this whole thing turns out to be 0, plus c. And cosine of 0 is 1. So then we have negative 6 equals negative 12 plus c. And solving for c, we end up with 6. So our final expression for the temperature would be minus 12 cos 2 pi over 365 t plus 6. So now we're in a position to determine the temperature on June 1st. We just need to figure out how many days it is after January 1st. In January, not including January 1st, because that would be time 0, there's 30 days. In February, there's 28 days, unless it's a leap year, then it'd be 29. For March, there's 31. April, there's 30. May, there's 31. And then June, we have that one day. So if we add up all these days, we get a total of 151 days. So June 1st is 151 days after January 1st. And now we just plug 151 into our expression for t. So negative 12 cos 2 pi over 365 times 151 plus 6. And it would be a good idea to make sure you're in radian mode, otherwise you'll get a temperature like negative 5.99 or something, which I totally didn't do. So we put negative 12, and if we evaluate this cosine, it works out to be about negative 0.856 plus 6. So total, we end up with 16.3 degrees Celsius. That's the temperature on June 1st according to this function. So in example number 2, the differential equation here, which we've seen before, represents the velocity of a stone thrown from the top of a building t seconds after release. If the stone is 60 meters above the ground 2 seconds after it was released, then determine when the stone will hit the ground. So we've already determined where this derivative came from. It came from the expression negative 5t squared plus 15t plus c. If you take the derivative of this, it will give you that expression. Now we have some additional information given to us here. It's 60 meters above the ground 2 seconds after it was released. So that means h at t equals 2 is equal to 60. So we can take that information and feed it in here to figure out what this c actually is. So h is 60 when t is 2. So everywhere you see a t, write a 2. So 15 times 2 plus c. And now we can figure out what c is because we only have one variable in this equation. So it'll be 60 equals minus 20 plus 30 plus c. Minus 20 and 30 combine to give 10 plus c. And finally, c is equal to 50. So that means in our expression here, c is 50. So now we need to figure out when the stone will hit the ground. And what is the height when the stone hits the ground? Height equals 0. So we can use our expression here, now that we know c is 50, and sub in a 0 where we see an h. So starting with negative 5t squared plus 15t plus 50, we need to figure out what time is when the height is 0. So next we can factor a negative 5 out, leaving us with t squared minus 3t minus 10. So we need to find two things that will multiply to give negative 10 and add to give negative 3. So we could use negative 5 and 2. Now this would give a time of negative 2 seconds, which is not really physical, so we eliminate that solution. And this one gives a time of 5 seconds. So 5 seconds is when the stone will hit the ground. So example number 3 will be the last one we go through together today. Find the equation of the curve that passes through pi over 12, root 3 over 4, if the slope of the curve at any point x is defined by sec squared of 4x. So we can call the curve maybe f, and the slope of the curve is defined by this function. So this would be the derivative of the curve that we're interested in. And this bit of information tells us that f at pi over 12 is root 3 over 4. So where did this derivative come from? That would be 1/4 tan 4x plus c. So if you take the derivative of this, that will give you sec squared of 4x. And now we can use this condition on f to figure out what c is. So everywhere we see an x, we're going to put a pi over 12, and everywhere we see an f, we're going to put a root 3 over 4. So root 3 over 4 equals 1/4 tan at 4 times x. So if we're doing 4 pi over 12, that's equivalent to pi over 3 plus c. Now because tan is defined as sine over cos, what we can do is sine at pi over 3 divided by cos at pi over 3. So sine at pi over 3 divided by cos at pi over 3. Sine at pi over 3 is root 3 over 2, and cos at pi over 3 is 1/2. So that would be equivalent to root 3 over 2 times 2 over 1, which is just root 3. So we can replace tan pi over 3 with root 3. So next we have root 3 over 4 equals root 3 over 4 plus c. Now if we solve for c, we need to subtract root 3 over 4 from both sides, and we find out that c is equal to 0. So ultimately, the function is going to be 1/4 tan of 4x, and that's it. This is our function that passes through this point, and the slope is defined by this. So now it's your turn. I'd like you to do example number 4 and try out a few questions from the textbook. That's it for today. See you next time.